Today we will start the second lecture of the course, which is Introduction to the Probability. So, probability as a relative frequency. Before we will start probability as a relative frequency, we will briefly summarize the lecture 1. In lecture 1, we talked about the probability, and we say that to define a probability, we are having two definitions. One is the probability using sets, or we can say the axiomatic definition of the probability, and the another one is a relative frequency definition. So the first definition that we talked in the previous lecture was based on the set theory, where we talked about the different sets. We said a particular set which is called as a universal set. We talked about subsets, disjoint sets, and in the end we talked about the axiomatic definition of probability, where we talked about the three axioms of the probability, which are that the probability of occurrence of an event is in between 0 and 1. The second one is that the probability of a sample space is equal to 1, and the probability of union of disjoint sets is equal to the individual probabilities of the events. Now we will be talking about a probability as a relative frequency. Before we will be talking probability in terms of relative frequency, there is another definition of probability which is called as the mathematical definition of probability. The mathematical definition of probability states that probability can be obtained as the ratio of the favorable outcomes to an event to the total number of possible outcomes. As an example, if we'll be tossing a dice, or if we'll be tossing a coin, and then if we'll be talking about the probability of occurrence of an event head in tossing a coin, or probability of occurrence of tail is equal to 1 by 2, which is because the number of chances of occurrence of head in tossing a coin is equal to 1, and the total possible outcomes are 2. So the ratio of the two will yield us 1 by 2. So we will be saying the probability is 50%. Or in case of tossing a dice, if we are asked what is the probability of occurrence of 1, 2, 3, 4, 5 or 6, so we can say it's equal to 1 by 6, because the probability of occurrence of any of the faces is just 1 and the total possible outcomes is 6. So the ratio of the two will yield us the result as equal to 1 by 6. The thing will get more clear if we are tossing a dice and we are being asked to find out the probability of occurrence of an even number. So here we are defining a subset, or we are defining an event as an even number. So the number of possible outcomes for an even number in tossing a dice is 2, 4 or 6. So we'll be having 3 possible outcomes for this particular event, and the total number of outcomes is 6. So the mathematical definition of the probability will yield the result as the ratio of 3 and 6, which is equal to 1 by 2. So in tossing a dice, we will be having the 50% of probability of occurrence of an even number. Then we talk about another definition of probability, which is the relative frequency. So this is basically the relative frequency of occurrence of some event, or we can say it is an estimate of the probability of occurrence of an event, which can be obtained by looking back at experimental or statistical data to obtain the relative frequency. So it can be differentiated with respect to the mathematical definition of frequency as that this probability is obtained from the data that has been obtained for a particular experiment. That is, if we are performing the same experiment of tossing a coin or of tossing a dice, we will be having a result over a wide range of experiments being performed, and that will suggest us what is the probability of occurrence of any of the events, which can be head, tail, or which can be in terms of this dice. It could be 1, 2, 3, 4, 5 or 6. So what is the probability of occurrence of one over a long period of time if the same experiment is performed again and again? So it can be given as equal to the number of times that particular event has occurred, the ratio of the number of times that the event has occurred to the number of trials. Then comes another probability, which is joint probability, which is defined for two events A and B which are not mutually exclusive. So the mutually exclusive events are those events which suggest that if an event A has occurred, it precludes that the event B will occur simultaneously. That is, if one event has occurred, the another event will not occur at that particular time. So those two events are called as mutually exclusive events. But the joint probability is defined for the events which are not mutually exclusive. Then the probability of the joint occurrence of the two events is called as the joint probability, which is given as the probability of intersection of the two events A and B, which is equal to the summation of the individual probabilities minus the probability of the union of two events. Equivalently, which can be written as equal to probability of A union B is equal to probability of A plus probability of B minus the intersection of the two, the probability of the intersection of the two, which can suggest us that the probability of two events which are not mutually exclusive A and B, the union of the two events will be either equal to or less than the individual probabilities of the two events. So for an example, the joint probability can be defined for the same experiment, that if we are tossing a dice and we say the two events defined are 2 and even number, we say that one event is the occurrence of phase 2 and the other event is the occurrence of an even number. So we can see that the two events are not mutually exclusive because the two events can occur simultaneously. We can have an event occurring as 2 and simultaneously it will be the other event also, which is the occurrence of an even number. So after joint probability, there comes another probability which is called as the conditional probability, which states that if we'll be having an event which is having a non-zero probability, that's it is having probability greater than 0. Suppose for an event B we define probability of B is greater than 0. The conditional probability of an event A given B, that means the B has occurred, is given as probability of A by B, which suggests the probability of occurrence of event A if B has already occurred is given as equal to the ratio of the probability of A intersection B to the probability of B, the event that has already occurred. So it suggests that the two events are dependent upon each other. That is, one of the events has occurred and what is the probability of occurrence of the other event depending upon the first event. So we can have an example here. We say if a fair dice is tossed, that means that it will be having the faces as 1, 2, 3, 4, 5 and 6. The conditional probability of getting 1 given that an odd number has been obtained. So we can say that we'll be having a sample space defined over the range 1 to 6, which are having the values 1, 2, 3, 4, 5 or 6, and the two sets defined here are as 1 and 135. That is, one is an event which suggests the occurrence of 1 and the another event suggests the occurrence of any odd number which is 1, 3 or 5. Then we say what is the probability of occurrence of 1 if A has already occurred. What is the probability of occurrence of 1 if the event A has occurred? Means that we can have either of the values 1, 3 or 5. So A has already occurred, some odd number has already reflected on. Now what is the probability of occurrence of B? So we can say that it can be calculated as the probability of A intersection B to the probability of, so it can be calculated as the ratio of probability of A intersection B to the probability of A. So A intersection B, which is only 1. So what is the probability of occurrence of 1? If we are tossing a dice, what is the probability of occurrence of a value 1? So it can be calculated as equal to 1 by 6, because all the values 1, 2, 3, 4, 5 or 6 will be having the probability of equal to 1 by 6. The second part is the probability of A. So the probability of A can be obtained over this particular set, which is either of the values 1, 3 or 5. So the probability of the event A of having 1, 3 or 5 is equal to 1 by 2, because the result is basically 3 by 6. So it is the ratio of 1 by 6 to 1 by 2, which will yield the result as 1 by 3. Then we talk about the properties of the conditional probability. If the first one is that if A is subset of B, then probability of B if A has already occurred is equal to 1, because this will be obtained as the probability of A intersection B divided by the probability of A. So the probability of B intersection A will yield us probability of A divided by probability of A, which will yield us the result as equal to 1. Here we can see that A intersection B is equal to A because A is subset of B. So if we're defining the second property, that if A is subset of B, then how probability of A if the B has occurred can be obtained. So it can be simply calculated as either equal to or greater than probability of A, because this will yield us the ratio of probability of A divided by the probability B, which can be either greater or equal to A. Then the third property is if A and B are mutually exclusive events which suggests that their intersection is 0, so probability of occurrence of B if A has occurred will simply yield us the result as equal to 0. Then if the two events are defined such that the probability of A is greater than the probability of B, then the conditional probabilities of the two events if the other event has occurred is given as the probability of A if B has occurred greater than the probability of occurrence of B if A has occurred. So the last property of the this conditional probability is that if A1 is subset of A2, then the probability of occurrence of A1 over the occurrence of probability of occurrence of B. That is, if B is defined as yet another event, then what is the probability of occurrence of event A1 if B has occurred? It will be less than or equal to the probability of occurrence of A2 if B has occurred. So we are defining here some other event B, then we are defining the conditional probabilities of the occurrence of two events A1 and A2 where we say that A1 is basically a subset of A2, the conditional probabilities again suggest that the probability of occurrence of A1 will be less than or equal to the probability of occurrence of A2 if some event B has already occurred. Then comes another term, which is independent events. So the independent events are defined as a set of events where the occurrence of one of them does not depend on the occurrence or non-occurrence of the other. So it's to be understood here the difference between the two. One is mutually exclusive events and another is independent events. Mutually exclusive events are the events where we say that if one of the event has occurred, the other event cannot occur. And the independent event suggests that if one of the events has occurred or it has not occurred, will not have any effect on the occurrence or non-occurrence of the other event. So we can say that if the probability of A, if B has occurred, is not having any effect on the event, on the occurrence of event B, it can be simply said that the probability of occurrence of A if B has occurred will be simply equal to probability of A. So from the conditional probability statement we can say that probability of A if B has occurred is given as equal to probability of A intersection B divided by probability of B. So if we'll be cross multiplying it, we will be obtaining probability of A multiplied by probability of B is equal to probability of A intersection B, and this statement will be governing that the two events A and B are independent events. If probability of A intersection B yields us the individual products of the two probabilities, then we say the two events A and B are independent events. Then we talk about the two theorems based on the independence of the events. We say that if the events A and B are independent, then the events A complement and B, or we can say A and B complement, are also independent. So the proof of the statement is given as that the events A intersection B, which will yield us the common values of the two events A and B, and A complement intersection B are mutually exclusive. The two events are not having any of the elements common, and the union of the two will yield us an event B. Therefore we can say that the probability of A intersection B plus probability of A complement intersection B will yield us the probability of B. So interchanging the terms, we will be obtaining probability of A intersection B is equal probability of B minus probability of A intersection B. Now here we have already defined that the events A and B are independent. Therefore probability of A intersection B can be written as the individual product of the two probabilities, probability of A and probability of B. So it can be obtained as equal probability of B whole 1 minus probability of A, where we can say that 1 minus probability of A will yield us the probability of A complement. So in the end we are obtaining probability of B multiplied by probability of A complement, which suggests that the two events B and A complement are also independent events. Then the other theorem is that if the events A and B are independent, then the events A complement and B complement are also independent. So this can be obtained like if we'll be talking about the probability of A union B whole complement, which can be put as equal to 1 minus probability of A union B. Now we know that probability of A union B is equal to the summation of individual probabilities, that is probability of A and probability of B, minus the probability of A intersection B. Now we know the events A and B are independent, so the probability of A intersection B can be given as the product of probability of A and probability of B. Then we can obtain it as equal to 1 minus probability of A minus probability of B whole 1 minus probability of A. So it can be obtained as equal to 1 minus probability of B multiplied by 1 minus probability of A, which can be obtained as equal to probability of A complement and probability of B complement. So we have obtained the product of the probabilities of A complement and probabilities of B complement, which will simply suggest that probability of that the two events A complement and B complement are also independent. So this marks the end of the unit. This marks the end of lecture 2.